So this is Dr. Keith Schubert. This is a video lecture on conditional sum adders. So this is just a help out for my students in 3338 as they're trying to figure out how all this works. So I've kind of given a little sketch here of how a conditional sum adder looks like with some little additions along the way where I can put calculations. FA, these are full adders, and then we break down the bits. Instead of doing the normal way where you're going to kind of ripple the carries in, we're either going to assume at any stage that the previous stage generated a 0 or a 1. So we'll generate both what if it didn't get a carry and what if it did get a carry. And we'll do that for each one. What if it didn't get a carry? What if it did get a carry? So we can do all of these calculations in parallel. Now we'll be doing almost twice as much work. I say almost because technically on the first one we know what it is, so we can just actually calculate that one here. And then since I only have one answer, what we can do is after we've done this calculation, we know what that carry was. I've got a carry and a sum bit, so I can use that carry to select was it a 0 or a 1, and I pick the answer. And I in essence throw the other one away, so I just use a multiplexer and I append the sum bit from the first area to the sum and carry of the second one, whichever one I happen to choose, either this one or this one, and that gives me my 3 bits that are here. I can do the same thing over here, but I don't know which of these two it is, so I have to select for both. So I'll both use this to select which of these two, if it had been a carry of 1, which will give me this one, or if it had been a carry of 0, which there is my carry out bit, and that'll select the next one. So I'll get both. And then, since this one is the true carry bit that should have come in, either 0 or 1, I can then again pick between them. So you can kind of see if I keep doing this, I'll just get a series of these multiplexers, each one just reproducing chunks as it goes and selecting them down. Since it's pairing them in binary, it'll make a binary tree, and therefore log base 2. So let's consider this for a calculation. So let's say, for instance, I was going to add 6 to, let's say, 5. Just pick a number. So we know normally we would go 0 plus 1 gives me a 1, carry a 0. 0 plus 1 plus 0 gives me 1, carry a 0. 0 plus 1 plus 1 gives me 0, carry a 1. 1 plus 0 plus 0 gives me 1, carry nothing. And so what I get at the end is 11. Works quite nicely. Let's see how this same thing, that's kind of ripple carry, and you can see I had to go through the whole thing, each one carrying through. Now when I'm breaking them up here, I'm going to take the 2 zeros, that's my bit 3s. And then I've got a 1, 1, and then I've got a 1, 0, and then I got a 0, 1. Now each of these is happening in parallel, so at this next stage they'd all be simultaneous. So I'd get 0 plus 1 into my full adder with whatever my carry in is. My carry in was technically a 0. So in this case I'll get 0 plus 1 plus my carry in of 0, and I will get 0, 1. Now that was the carry bit, and 1 the sum. Now for this one, since I didn't know it was going to be a 0, which will be this side, I have to calculate both. So I'll go in 1 plus 0 plus 0, and I get 0, 1. I will also get 1 plus 0 plus 1, and I'll get 2. Same thing here, except with different numbers. Again, since I don't know the carry, I have to do 1 plus 1 plus 0 gives me 2, and 1 plus 1 plus 1 gives me 3. And for the last one, again, don't know, so 0 plus 0 plus 0 gives me 0, 0 plus 0 plus 1 gives me 1. Now those would all be generated at the same time, so it would take the same speed as just doing one, no need to ripple. But I haven't picked the final answer yet. So now at the time when you'd be handling the second bit here, I can combine those together. So at that point this 0 would come in and it would select this one, which would be the 01. So I get 0, 1, 1. Now that's the result, the 1, 1, carry a 0. That's exactly what we have. Same thing happens here, except I do it twice, but they're in parallel, so it doesn't take any extra time. So 1, 0. So the 1 is going to select this one here, which is 0, 1. 0, 1, 0. Now, if it had been this one, the 1 would also select 0, 1, but this time the appended bit would be a 1. Now, when we look at this, in reality, so that's what happens at the same time this bit's being calculated. Now, at the time I'm going to the third bit, I'm getting my answer, whereas here I'd have to wait for the fourth. So what I can do now is just take these, again, 0 selects this side here, so that's 0, 1, 0, and then 1, 1. And you notice I get the same carry bit, both 0, that's the carry out, then 1, 0, 1, 1, 1, 0, 1, 1. So it works perfectly no matter which way it goes. If you had flipped one of the numbers and had a carry in of 1, you'd be doing subtraction. It would still work the same. So this is just a slightly faster way. This one, since it is doing the binary tree, means it's going to be proportional to log base 2 of n, as opposed to the ripple carry adder, which is, so this is big O of, that's for my conditional sum. If I had been doing the ripple carry, I would be big O of n. So it gives me a faster one, and as the bits increase, it becomes quite significant. So if you think about, you know, for a 32-bit number, this is 5, and that one's on order of 32. So it's a significant difference. As you go up to 64, it gets even bigger, 6 versus 64. The constant on this one is about 2. You know, so even if you're dealing with a constant of 2 or so on this side, you're still tremendously ahead of the game. So just a nicer way of doing it, a very simple, elegant circuit that can exploit these things. So hopefully it makes sense. There's some more examples inside my notes for the class, so you're welcome to look those over, but hopefully the circuit makes sense to you now. Have a good day.